Okay, we're going to continue on here in chapter 4. And last time, a week ago, we talked about something, I think. We talked about atomic number, I believe. And remember that the atomic number is the number of protons there are in an atom. We also talked about the mass number, which is the number of protons plus the number of neutrons. And remember that those numbers are important because you could use both of those numbers, the mass number and the atomic number, to figure out how many neutrons there are in an atom. Again, you could take the mass number minus the atomic number, and that will give you basically your number of neutrons. When we look at the periodic table, we do have the atomic number on there. And remember that the atomic number, which again is the number of protons, is really an important number because that is really what determines what element you're dealing with. So as we talked about last time, if you look at the periodic table, there is no atomic number that repeats, which means every element has its own identifying atomic number or number of protons. So again, if you know the number of protons or the atomic number, which is essentially the same thing, you will know what element you're dealing with, or vice versa. If you know the element, you could just go to the periodic table and you can simply figure out how many protons it has or what its atomic number is. Also, a reminder that the mass number is not on the periodic table. That is not the mass number down there. That's the atomic mass, which we'll talk about next. But that is not the mass number. Remember that what we talked about was that when you do the mass number, atomic number, number of protons, electrons, and neutrons, they all should be basically positive whole numbers. And clearly, if you look at the periodic table, none of those numbers on the bottom there are pretty much, they're all decimals for the most part. And that is actually the atomic mass, which we'll talk about in just a second. And again, like I talked about last time, what sometimes confuses people is the atomic mass on the periodic table and like the mass number are very close numbers. So sometimes people just think, oh, they just rounded the number that you see on the periodic table. So once again, that is not the case. When you're asked these problems like we did the other day, you should have enough information given to you to figure out protons, electrons, neutrons, mass number, and atomic number. And again, they all should be pretty much whole numbers. Clearly, before this, we talked about some experiments and really the model of the atom, right? And basically, the atom, right, has a nucleus in the middle, which makes up most of the mass of the atom. And inside the nucleus is our protons and neutrons. So we have protons, which are positively charged particles. We have neutrons, which have no charge, and those are in our nucleus. And out in that empty space that Rutherford found, we have our electrons, again, moving around pretty randomly in that empty space. Remember that when we kind of look at those three sort of subatomic particles, protons, electrons, and neutrons, it is actually the neutron that is the heaviest of all of them. The proton's pretty close to it. If you go out a few decimal places, the neutron beats it. But the proton and neutron are both pretty much about 1,800 or so times heavier than any electron that's flying around. And again, that, as we talked about last time, is pretty much what Rutherford said. That's a nucleus, basically, what makes up most of the mass of the atom, because that's, again, where we find our protons and our neutrons. And our electrons are basically flying out in that empty space. There is some of that electrostatic attraction, opposite attraction between the negatively charged electrons and the positively charged the positron nucleus, and that's what kind of keeps the electrons from just flying off. Also, as we will talk about, that is also why certain electrons, again, are involved in things like bonding versus other ones that are not involved in bonding based on sort of their location to the nucleus. And that is also why in normal chemical reactions, like we talk about in this class, we never change the element. There's always conservation of the element because the only thing involved are the electrons when we do a chemical reaction. We do not touch the nucleus, and because we don't touch the nucleus, we don't play with the protons, and we never change the elements, right? So that's, again, why if you started with 3 carbons, you should end with 3 carbons. They may be in different compounds at the end, but you won't change elements because of that. Dare I say, we talked about some ions. I seem to vaguely remember that towards the end there. And we talked about ions, and ions are things that have charges. And there's really two types of ions. There are cations, which are positively charged. Remember that basically you get a positive charge ion by losing electrons, basically. And in that situation, when you lose electrons, you then have more protons, which are positive, than negatively charged electrons. And you end up with a positive charge in that case. We also have anions. And anions are negatively charged guys, and that's a result of gaining electrons. And once again, same sort of idea. When you gain electrons, you then end up with more negatively charged electrons than you do positively charged negative charge. The only thing that does change, as we talked about, when we're doing protons, electrons, and neutrons, is if it does have a charge. Once again, it is the electrons that does change. The actual charge value or number is really how many electrons it changes from, say, the neutral. So, a sodium has 11 protons and 11 electrons when it is neutral. And sodium, when it does gain a positive 1 charge, would still have 11 protons. Otherwise, again, it would not be sodium. And it would have 10 electrons. And again, 11 positives and 10 negatives gives you that +1 left over. That is the charge. The difference here between the neutral sodium and the sodium with a +1 charge is it lost 1 electron, which is what the charge is, +1. So the positive charge means you lose electrons. The number is how many electrons you lost from the neutral sort of atom in that case. And it works the same way with our negatively charged guys. So if we take oxygen, oxygen is 8. It has 8 protons and 8 electrons in a neutral oxygen. Oxygen, when it gains a charge, will become a -2 charge. And that still, again, has to have 8 protons. Otherwise, it will not be oxygen. And in this case, it will actually have 10 electrons. And that gives us an overall -2 when we take 10 negatives and 8 positives. And once again, that is where the charge comes from. And in comparison between our neutral guy, which is 8 electrons, to our -2 guy, which has 10 electrons, the difference is 2 electrons. Negative means it has gained electrons from its neutral self, if you will. Any questions on that stuff there? By the way, also, I think we mentioned it, but doesn't hurt one more time. If you take anything from the periodic table by itself that's uncombined, not with anybody else, just by itself hanging out, it does not have charges. And actually, things only get charges when like the metals and the non-metals start to hook up with each other. That's basically where we get these transfer of electrons. And typically speaking, it is the metals that will lose the electrons and become cations, and it's the non-metals that basically will pick up those electrons and become anions. And that's essentially what happens. So for example, sodium would give away an electron to a chlorine. Chlorine would pick it up, and now you have a sodium ion and a chloride ion, opposite attraction, ionic bond. They come together, and that's what will hold that together. Any questions on that? All right, then let us continue on maybe, huh? All right, so we talked about isotopes as well. And remember that, again, isotopes are really the same element, but they do have different masses. So once again, because they're the same element, they have the same number of protons. They have different masses because they have different numbers of neutrons. And we also write our isotopes in this fashion, where we put the mass number up on top and our atomic number bottom left there, right? When we kind of write out our symbols for it. In most cases, neutrons don't take part in normal chemical reactions, as I was just mentioning. It is just the electrons, and that's really helpful. So for example, you can use, for example, an isotope of an element that may be radioactive, and you could actually just follow what it normally would do in, say, a process. I used to do like copper-64, which is the radioactive version of copper. and we were interested in where copper went in a mechanism in the sort of the body. And you can use a radioactive version of it. It will do the same chemistry as non-radioactive version of, say, copper, and you can just follow the radioactivity and figure out exactly where the copper ends up, where it goes through the certain process or pathway. So sometimes isotopes are used for that sort of purpose. They're very helpful, again, because they will do basically the same chemistry as, the sort of regular old element that may be not radioactive. Not all isotopes are radioactive, by the way, but a lot of them are. All right, then let's talk about chemical composition, and let's talk about really the other number there that people want to always use for the mass number, and that is atomic mass. And the atomic mass is what you find on the periodic table there. It is that number that is underneath the symbol. And obviously, one of the fundamental properties of an atom is its mass. And since an atom pretty much is made up of three things, protons, electrons, and neutrons, it's related to how many of all those guys that you have. But obviously, an atom's extremely small. You can't really just pick one up and pop it on a scale or anything like that and basically measure the mass of it. So usually in chemistry or in science, when you cannot directly measure something, a lot of times what they will do is assign somebody to be used as a standard to compare everybody else to. And in terms of atomic mass, they actually use an isotope of carbon as the standard sort of guy to compare everybody else to. They use the carbon-12 isotope, and the carbon-12 isotope has a mass of exactly 12, what is referred to as AMU. AMU is atomic mass units. It is essentially units that, I don't really want to say it like this, but it's units that we probably don't use all that much anymore, but they are the units. And technically speaking, when you look at the periodic table for all these numbers that you see on the bottom, one way that you could look at it is, for example, if you look at hydrogen, it says 1.008. That would be 1.008 AMU in an atom is sort of the units that you can use it for. We will talk about in a later chapter a more usable sort of unit that involves grams, and that's what's known as the molar mass. And as we will talk about later, it's essentially the same number as well. But you can take that number off the periodic table as how many AMU there are in one atom of whatever you're looking at. Obviously, if you looked at oxygen there, 16, that would mean that there are 16 AMU per atom of oxygen, basically, there from the periodic table. So this carbon-12 isotope has exactly 6 protons and has a mass of exactly 12. And basically what they did is some experiments and said, well, for example, hydrogen is only about 8.4% as big as the carbon-12 isotope. So they basically do a little calculation here. That is 8.4%. Convert it into a decimal, divide by 100, or move the decimal place 2 places to the left. You times it by 12, you get the mass that you see there on the periodic table. Similar calculations have been done for all the elements there on the periodic table. Now, one of the interesting things that you might think of is, well, if they use the carbon-12 isotope as the standard, and it has a mass of 12.00, why, when I look at the periodic table, does carbon say 12.01? And there is actually a reason for that. And the reason for that is what we actually see on the periodic table are what are referred to as the average atomic masses of all the naturally occurring isotopes for that particular element. Although most people don't call it average atomic mass, but that is essentially, what you are looking at in that particular case. So they could actually do a calculation to do that and figure out what they get on there by taking the atomic mass of a isotope is equal to the percent abundance of that isotope times the atomic mass of, say, isotope, I'm just gonna call it isotope I number 1, and the percent abundance of isotope number 1. Then you add it to the percent abundance of isotope number 2 times the atomic mass of isotope number 2. And you basically continue that pattern. And the important thing here is actually it's adding. And when people do this calculation, they always want to multiply that. So it's actually adding there. And people always, again, seem to want to do that. What is percent abundance? It's sometimes called relative abundance. Is basically the percentage of time that that particular isotope appears in nature, basically. Yeah. So for example, carbon, there's a carbon-12 isotope, carbon-13 isotope. One appears about 98% of the time, one's about 1% of the time or so. And that is basically the percent abundance here. When we do multiply in this equation by the percent abundance, you do need to convert it into a number, if you will, or a decimal. So again, you can either move the decimal place 2 places to the left, or you could divide the percentage by 100 and it'll move the decimal place for you. So whichever way you want to do it. But you probably, in most cases, when you go do this calculation, you should not leave it as a percentage. So you kind of have to convert it into a decimal, yeah, on both of those. And again, if you did have 3 isotopes, you just kind of continue this pattern, or 4 isotopes, or however many isotopes you get. So if we take a look, for example, at carbon here, and just to explain what we were just talking about, we see that there's a carbon-12 isotope. It has a mass of 12 AMU. It occurs about 98.97% of the time. We also have a carbon-13 isotope, which has a mass of 13.003 AMU, and that occurs about 1% or so of the time. So if we were going to do this calculation, you would take the atomic mass, and we take our first isotope. And once again, it's up to you how you want to do it. You can take the 98.97% and just divide it by 100 to move the decimal point for you if you wanted to do that. And you could times it by the 12 AMU. That's basically our first isotope there, information. Once again, as I mentioned, we're going to add here, not multiply. And we're going to do the same thing for our second isotope, which is this guy. And if you want, you could not divide by 100 and just simply move the decimal point and over 2 places to the left, and you could do that as well. And again, we're going to multiply that by 13.003 AMU. And again, you can see here, you will end up with 12.01, which is the number that you see there on the periodic table. So again, what we do see on the periodic table is the average atomic masses of all of the naturally occurring isotopes for that particular element. Any questions on that there? Yeah. It will. Well, I put it this way. It should be close to 100, and you're absolutely correct. Some of the problems that you come across, they may not equal perfect dead on 100 based on rounding and stuff like that, but it definitely should be in the ballpark of 100. So I don't know what this one comes up to, but we're a little bit perhaps over on that. So, or a little under. So you may be like 99 or maybe 101-ish or something like that, but it should be in the 100% sort of region. And it may not always be perfect 100% because of rounding and stuff like that. Now, that's also a really good point. If you come across a problem, for example, where maybe you're given the atomic mass of the element and you're given, for example, one isotope's percentage in atomic mass and maybe just the atomic mass of the next isotope, right? You could figure out the percentage by assuming 100, right? And kind of subtracting from 100 and figure out what the missing percentage is. So you do want to, when you do these type of problems, kind of add up the percentages and make sure you are near 100 or pretty darn close with rounding near 100. If you're not, then you're probably missing an isotope somewhere. Yeah, so there should be some information to allow you to solve for that as well. Other questions? All right, so why don't you try one here? We have bromine's got 2 isotopes. Bromine 79, 50.70% of the time, and bromine 81, 49.32% of the time. The atomic masses of each of those guys 78.92 and 80.92 respectively. What is the atomic mass of bromine? Back for just a second to this one, and involving carbon. And just to remind you as well, another really important point. Again, that is the average atomic mass of 12.01, which means if you had a bunch of carbon atoms together and you could individually kind of pluck out each of the carbon atoms, you would never find one that has a mass of 12.01. You would find one that's either the carbon 12 with a mass of 12, or you would find one that's the carbon 13 with a mass of the 13. Again, this is just an average value that we do use. But in reality, if you could kind of pluck them out individually, you'll never really find one with 12.01. It's either going to be the carbon 12 or carbon 13 sort of isotope. All right, so with that being said here, we're going to find our atomic mass. So we're going to use our formula. We basically have, in this case, two isotopes. We have bromine 79, which has a percentage of 50.70%. And it has a mass there of 78.92 AMU. We also have bromine 81 that occurs about 49.32% and has a mass of 80.92 AMU. So as was sort of the earlier question here, if we just quickly kind of add together our percentages, in this case, we're at 100.02, again, pretty much 100. So we definitely have all of our isotopes there. We're not, missing anything. So to do our calculation here, our atomic mass going to be, again, I'm going to move the decimal point on the first one. So 2 places to the left, converting that percentage into a decimal. And I'm going to times it by the atomic mass of our first isotope there. So that's basically our first isotope. Again, we're going to add, not multiply here. And on the second one, if you want here, I will divide by 100%, which again will move the decimal point for you. So it's, again, your call, kind of whichever way you want to do it. But whichever way you do it, you do need to do it one of those ways to get it into sort of a decimal form. And if we do all that good stuff and punch that in, looks like 79.92 AMU there is going to be our winner. And that would be, obviously, it looks like this guy right there. And that's pretty close to what we do see here for bromine, 79.90 in this particular case. Yeah. Any questions on the calculation there for atomic mass? Yeah. How did I get? I'm sorry. Yeah, so it's basically just converting a percentage into a decimal. So basically, to do that, you're really dividing by 100, and that will get you your 0.5070. Alternative to that, because basically you're going to divide by 100, you could also just move the decimal point 2 places to the left to convert it into a decimal. Yeah. Yeah, so it's a good question, actually. Typically speaking, when we do take the atomic mass off the periodic table, and later when we use really the same numbers for molar mass as well, typically speaking, when you do it, it's usually 4 significant figures is typically where you want to go to when you're calculating anything like atomic mass or molar mass, like we're going to do later. So, and even if you take it off the periodic table, again, 4 significant figures, depending on the periodic table that you're looking at, they maybe have a lot more numbers or less numbers, usually more numbers, but usually rounding wise, usually you would also take kind of 4 significant figures is sort of what you're looking at. Yes. You don't. I just showed you both ways you could do it. Absolutely. So in this one, you could have, instead of what I did here, you could have just did 0.4932 times 80.92 AMU. Yeah. Yeah. So that's basically what this will get you. So I was just showing you can do it either way that you want. And again, I would just pick one way and do it for both, but I was just kind of showing you both ways that you could get to the decimal. Yeah. Other questions? Okay. All right. Speaking of the periodic table, let's officially talk about the periodic table. That's a periodic table. Look at that. That's a periodic table right there. So the periodic table obviously has a lot of information on it, and we're going to talk about the different important parts to the periodic table. Let's get into that. So first off, elements that are in a column on the periodic table, they are referred to as a group or a family. If you're really old like me, nobody calls it a family anymore. Most people call it a group, I think. I don't even think they put family in books anymore. But group is pretty much what most people roll with these days. And when you look at the periodic table, for example, the one that's up there, or even the one that's on the wall here, there's actually a bunch of different numbers that you see up on top. So there are what are sometimes referred to as A numbering, there are B numbering, and then there's just straight up 1 through 18 across the top as well, just for good measure. So you'll oftentimes will see 3 different sort of numbering sort of up there on top of the groups. And what we use in this chemistry class, and pretty much every chemistry class you take for the most part, is the A numbering. And the A numbering is sometimes referred to as the representative numbering. And again, when we talk about a group, that is going down on the periodic table from top to bottom. And that means that group 1 is right here. Group 2 is right next door. And then we actually skip the middle part. And group 3 picks up over here. Group 4, group 5, group 6, group 7, and group 8. Now, they are technically 1A, 2A, 3A, 4A. Very few people say A after it. Most people just go group 1, group 2, group 3. But technically speaking, they are the A numbering that we do follow here. Yeah. We'll get into that a little bit later on. Yeah. So we go 1, 2, we skip the middle, we go 3, 4, 5, 6, 7. By the way, speaking of group 1, pretty much on every periodic table, as you can see up there and on the slide as well, group 1 does not include hydrogen. Group 1 actually starts with lithium. Lithium is the first member of group 1. There is a reason hydrogen's hanging out over there, and we'll talk about it in just a second. And speaking of being old, years ago, they used to put hydrogen actually on both sides of the periodic table. You would find it here and over there as well. They stopped doing that recently. But hydrogen is actually not part of group 1. It actually does start with lithium, and we'll talk about, again, why that is in just a second. Now, going horizontal on the periodic table, that is left to right on the periodic table, those are called periods. And on the periodic table, there are 7 periods, 1, 2, 3, 4, 5, 6, and 7. And again, they go, in this direction going across. We also have talked about it, the number that we see on top of the symbol, which, as we know, is the number of protons, as we've been talking about there. And again, every element has its own atomic number. Now, the periodic table is, and the elements are divided into 3 different categories. There are metals, nonmetals, and metalloids, which are sometimes called semi-metals. Pretty much on most periodic tables that you see, you can kind of see what is oftentimes referred to as a staircase coming down around boron. And that is kind of your dividing line, if you will. So to the left, you can actually see it here as well, coming down. To the left of that staircase, that is where we find metals. And metals are good conductors of heat and electricity. They can be hammered into thin sheets. They could be pulled into wires. They typically have a very shiny appearance. For the most part, all metals are solids at room temperature. The one exception is Hg, number 80. It is mercury, which is a liquid at room temperature. All other ones are pretty much solids at room temperature. If we look at to the upper right of that staircase, that is where we find nonmetals. And nonmetals essentially have the opposite characteristics of metals. They are dull, they're brittle, they are bad conductors of heat and electricity. Also different than metals is nonmetals come in a pretty variety of states. You have some nonmetals that are liquids, you have some that are gases, you have some that are solids. A lot of our diatomic molecules that are elements are nonmetals, pretty much all of them. That's our H2, our N2, our O2, our F2, Cl2, Br2, and I2. That is also why when we come over here to our periodic table and I put hydrogen there, that is why hydrogen is not part of group 1, because hydrogen is what type of element? It is a metal or a nonmetal? It is a nonmetal, hydrogen. Everybody else in group 1 is a metal, yeah? So that is why hydrogen is not part of group 1. It's actually a nonmetal. Everybody else in group 1 is a metal, is actually hanging out over there because hydrogen has some unusual properties, some of which behave very much like group 1 metals. So it behaves sometimes like a group 1 metal, but it's really not a metal. It's actually a non-metal. So that is why, like I said a second ago, years ago, they would sometimes slap hydrogen on both sides and put it over there with the non-metals where it kind of goes. But then it confused people why there's 2 hydrogens on the periodic table and stuff like that. But again, hydrogen not part of group 1 because it actually is a non-metal. Now, metalloids is that staircase that comes down. And just for an overlay there, you can kind of see coming through here is our semi-metals. And these are also sometimes referred to, like I said, as semi-metals. Metalloids have properties that kind of fall on both sides. So it is kind of in the middle there between metals and non-metals. So metalloids, one individual metalloid can have properties that people would say is very similar to what you find in metals. And the same one could have properties that are similar to what you find in non-metals. So it kind of makes sense. It's almost like a transition point as you go from metals to non-metals. So those guys, semiconductors, sometimes they have those properties kind of fall on both sides of sort of the staircase, if you will. The 2 rows on the bottom there, these guys are also metals. Yeah, so even though they're on the bottom there, they are metals down here as well. Now, these groups do have some special names, and you do need to know the names of these groups. So again, group 1, which once again starts with lithium, those are the alkali metals. Right next door in group number 2 is the alkaline earth metals. By the way, the word alkaline pretty much means basic. And that's where a lot of strong bases come from. Things like sodium hydroxide, potassium hydroxide, calcium hydroxide. They all come from group 1 and group 2 on the periodic table. So that's where a lot of bases come from, those groups. All the way over here to 7, that is the halogens. Those are also those diatomic guys are fluorine, chlorine, bromine, iodine that comes as 2s. And right next door on group number 8 is the noble gases. And the noble gases, noble means basically set apart. They are chemically inert, which means that they do not react with others. They will react with themselves, but they pretty much are very unreactive type of gases. By the way, those gases, your helium, your neon, your argon, your krypton, all your ons there at the end, they all come as monoatomic. They all come as 1s, basically. So unlike hydrogen gas, oxygen gas, nitrogen gas come as 2s. Those guys in the noble gases come as 1s. By the way, there's also some noble metals like silver, gold, and platinum. So these are what are sometimes referred to as noble metals there. Also very unreactive. Gold pretty much unreactive with anything. You could throw some pretty strong acid on it. It's just going to laugh and do nothing pretty much, yes. That's how they test, by the way, like if the gold's real sometimes they used to do that, throw some nitric acid on it. If it's still there, it's real. If it's not there, well, you didn't have much to sell at that point, right? So there's not as much left there at that point. Other things on the periodic table, the 2 rows on the bottom here are set aside so your periodic table is not giant. But if you follow the numbering in terms of atomic number, load up a little bit here maybe. That's 56, 57, and 72. There's 58. It actually goes right there, that row. And here, 88, 89, 104. There's number 90, goes right about there. These guys right here technically go right in that spot. They are called the lanthanide and actinide series because those are the elements on the periodic table they should follow. I've never really seen anybody put them in the right spot except for one place, and it takes up the entire wall because it pushes the entire periodic table to the right, so the entire wall gets taken up. But they actually technically go in that spot. Good news for us is we don't really deal too much with those two on the bottom, so probably not to worry too much about those guys. Last sort of spot there on the periodic table is between group number 2 and group number 3. This is the transition metals. Transition metals can have one of their properties, as we'll talk about when we talk about naming, is they can actually make a variety of charges. So for example, copper can make a +1 charge or a +2 charge. Iron could go +2 or +3. So they have the ability to kind of make a variable type of charge. That's also why, by the way, since these two on the bottom technically go right in that spot, the two rows on the bottom are sometimes referred to as inner transition metals because that's technically where they should be slapped in the slot on the periodic table. So those guys on the bottom are sometimes referred to as inner transition metals. Any questions on that there? So you do need to know, obviously, the periodic table. You need to know which way groups go. You need to know which way periods go. You need to know the names of the special groups. You need to know where transition metals are, where metals, nonmetals, and metalloids are found, and some properties of each of those. Any questions on that? Question? Mm-hmm. So it would normally be referred to as more of a general classification of like transition metal. But in that case, you would probably fall back to sort of the B numbering or just the regular old numbering, and technically it would be here in 8B or group 8 or 8B. So you know it's not that 8 over there. So how to give sort of the number for it, you would probably go to the kind of B numbering at this point. And then when you get kind of down over here, you'll kind of switch over, you know, kind of to the other one. So like that, yeah. Other questions? Bless you. All right, so now we're going to talk about really modern atomic theory and the periodic table, and really we're going to talk about electrons and as they transition, for example, from one energy level to the next. And what happens, for example, when we have electrons, say at different energy levels, and if this arrow is an electron, and each of those lines are different energy levels, when you excite an electron and you add energy to it, that electron is going to gain that energy and find itself at a higher state of energy, basically. And most things in chemistry, as you may know, or if you don't know, let's talk about it. The idea of most things in chemistry is that the goal is to get everybody to kind of the lowest state of energy. Kind of low state of energy is really the most stable sort of form of energy. A lot of things that happen in chemistry, it's all a lot of times in the purpose of getting everybody down to kind of a better state in terms of energy. So if you did something to this atom and that a higher energy state, what's going to happen is it's going to want to work its way back down. So this electron will try to work its way to a lower energy level. There's a law of conservation of energy which states we can't create nor destroy energy. So the atom itself, for example, would have to give off that energy in the form of a photon of light. And if that light has a wavelength that corresponds, for example, to the visible part of the spectrum where we see color, Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet, I hope, right? So you see color, you'll see actual colors. This is what happens with fireworks, right? They shoot off fireworks, they explode fireworks. That's a lot of energy on those fireworks. They have elements in there. Their electrons go crazy and they eventually work their way back down, gives off energy in the visible part of the spectrum, and we go pretty red color, right? Blue color, green color that comes off in terms of the fireworks because we could see those energy basically being given off. Same thing if you've ever done a flame test. Put your element into a flame, you'll see the color of the flame change as the electrons are excited. You probably have done a flame test without realizing if you ever boiled water on a stovetop that has a gas and fire and it overboils and it hits the water changes color, right? And that's like the sodium there, ions getting excited from the flame and changing to like that orangey color. It kind of comes for a second and then kind of goes away as it overboils. So not all not all sort of photons of light or energy that's given off will be part of a visible part of the spectrum where we can see it. Now, there is a relationship when we talk about photons, which are really waves, and waves look like that. That's basically how energy sort of transfers itself through space. And the relationship is if you have a long wavelength, which is sometimes abbreviated with the lambda symbol, that's what a wavelength basically is. You also have what is referred to as a lower frequency. Frequency is abbreviated with the new symbol, which people call a V all the time, but it's really not a V. And frequency is how fast, right, or how often a wave passes a point every second, basically. That usually results in a low energy type of situation. And that's opposite if you have a small wavelength. You will have a higher frequency, and that's usually higher in energy. So for example, instead of that wave there, we got something like this, right? A much smaller wavelength. By the way, the wavelength is between two peaks or troughs there in a wave. So this would be like my wavelength here. This really small spot right there would be that guy. So when we have this sort of energy being given off in the form of these waves, they can fall anywhere here on what is referred to as the electromagnetic spectrum. And this is where we see different sort of things occur. So on the left-hand side here, we have a longer wavelength. And on the other side over here, we have a really small wavelength. And that means on the left-hand side, this is a little bit lower in energy. And on the right-hand side here, that is very high in energy, where we have that really small sort of wavelength. So for example, we have things like radio waves here, which have longer wavelengths. So when you tune your radio, for example, to 95.5 megahertz, that is a frequency, right? Bringing in your radio waves to your radio. Yeah. Say it again. Oops. Sorry. There you go. There you go. Yeah. So the smaller the wavelength, the higher the frequency, because it's basically doing this, right? It's moving really quick. So it's going to pass that point a lot of times in a second, right? A longer wavelength, more drawn out, is going to kind of move, like this. Yeah. And it's going to not pass that point as often. Yeah. No, yeah. So it's kind of a similar idea. There's different spots and there's different categories within here. As you can see on this one, you got your AM, FM, you got some cell phones and television sort of waves coming in and that stuff. But in terms of this, we have radio waves, which again is a longer wavelength, kind of lower in energy. As you move down, we get to kind of microwaves, a much shorter wavelength than radio waves, a little bit more energy. So at that point, it has enough energy to kind of move your water molecules really fast in your food, and you cook your pizza in like 2 minutes, right? It's all good. Good technology. Then we have the infrared part of the spectrum. Again, lower, smaller wavelength, a little bit more energy is where we kind of feel heat and stuff coming off. And then we get to right here, which is the visible part of the spectrum. And that again is where we see colors. And that is where we see those colors of red, orange, yellow and all that stuff that I was just mentioning there. Got our red, orange, yellow, green, blue, a little indigo, and some violet happening there. And we will see color coming off in this part of the spectrum. So if you have a wave that's coming off based on some energy being given off that falls in that part, that's where we again will see colors like the flame test I was talking about, fireworks, whatever it may be. Even with colors, there is a difference in terms of energy. Red is actually a longer wavelength, about 700 nanometers, versus violet or purple is more like 400 nanometers. Which one should be higher in energy? Which one is the smaller wavelength, 400 or 700? 400, yeah. So purple actually is much higher in energy than red because red's at a longer wavelength. So even within colors, there is a difference in terms of the energy associated with those waves that are coming off. What does that mean in terms of transitions? We're talking about really electrons transitioning. If an electron transitioned a lot of energy levels, that atom would have to give off a lot of energy to allow it to come back down, right? And that would probably be more like a purple color if it was in the visible part of the spectrum, as opposed to if the electron just dropped like one energy level. Not a lot of energy difference between those two, would give off a smaller amount of energy with a longer wavelength, maybe closer to like a red in color, if it fell in that visible part of the spectrum. Next to that is ultraviolet, smaller wavelength yet. Again here, that is why we put sunblock on so we don't get too burnt, right, when we're walking around from the UV rays outside. X-rays, right? Smaller yet in terms of wavelength. Why they throw a lead vest on you and they leave the room usually when they shoot those X-rays, right? So they don't get too exposed because it's a lot of energy. And gamma rays, we talked a little bit about when we were talking about sort of those experiments on the atom. Those, that's basically pure energy. That's pretty strong energy. And if you do anything that's working with gamma rays, like radioactivity, you definitely want to make sure that you have proper sort of protection to do so. So again, here's just another sort of picture of what we were just looking at. You need to know, and you need to know that, on this side, again, longer wavelength, lower energy, and lower frequency. This side, again, smaller wavelength, higher frequency, and higher energy. So you need to know what's on, I would say, this picture. The other one has a lot more stuff on it. This is more of a basic picture of it. You need to know what's on here in terms of not exactly where everybody breaks off in terms of wavelength or anything like that, but you need to be able to put them in order, for example, from lowest energy to highest energy, longest wavelength to shortest wavelength, frequency and stuff like that. So that also includes, again, the colors. You need to be able to put in order from highest energy, lowest energy, wavelength, all that kind of stuff. So again, our Roy G Biv going on here in this case. So any questions on that there? And I would say these kind of basic ones here, I guess I should use a different color. Radio waves, microwaves, infrared, visible, ultraviolet, X-ray, and gamma. So those guys, yeah. Any questions on that? All right, so if we look at this, right, we want to identify the form of electromagnetic radiation that should have the greatest or the greater energy. So here, yellow light, blue light, blue, right? Again, blue is closer to purple, right? So that's going to be a shorter wavelength and higher energy. Ultraviolet, infrared, ultraviolet, X-rays, microwaves, X-rays. There you go. Yeah. So what happens with atoms when you heat them and these electrons start basically jumping around? It will give off what is referred to as a spectrum, and elements will give off what is referred to as a line spectrum. And they represent really the electrons transferring from one energy level to the next. and the energy coming off. It may again fall in the red part. You'll see a red line. Falls in kind of the purple part in the wavelength. You'll see a purple line. So basically, you can excite an atom, look at it through a prism. It will separate it out, and you'll get these distinct lines for elements that give a line spectrum. And elements give off basically very unique line spectrums to the point where, based on the lines that you see, the wavelengths that you see, the colors that you see, you could identify what element you're looking at. So everybody has kind of their own unique, almost like a fingerprint, kind of their own unique line spectrum pattern. And this happens really with elements because as electrons transition from one energy level to the next, they do so by doing what is sometimes referred to as a quantum of energy or a quanta of energy. And what that essentially means is when electrons get excited and they go up to a higher energy level, or even when they come down from a higher energy level to a lower energy level, they do so in a quantized fashion. And what that means is they will always gain enough energy to fully transition from one energy level to the next, or they will lose enough energy to fully drop from one energy level to the next, maybe 2 energy levels at a time, 3, 1, whatever it is. They will never find themselves like halfway between. Yeah, so they'll either lose enough energy or gain enough energy to make that transition. The simple sort of explanation of that is quantized energy stairs. Yeah, when you walk stairs, if you do walk stairs, you usually have enough energy to get to this step. Then from that step, you have enough to go there to there, right? And if you're coming down, you usually could go from one step to the next. You don't usually stop halfway through and go, I'll take a rest, right? Because you're going to fall. So that's basically how electrons transfer from energy level to the one energy level to the next. They will gain enough energy to fully transition either upwards in energy or downwards in energy. They won't find themselves in between energy levels. So they'll never kind of find themselves in between. Same idea with stairs, right? Some people maybe do 2 stairs at a time, right? And going up or down, or 3 maybe. Maybe not more than 3, I suppose. But again, same thing with electrons. They may transition one energy level, 2 or 3 or 4, depending on, what's happening. By the way, when a atom gains energy and this electron goes from a lower energy level to a higher energy level, is that endothermic or exothermic? Was energy absorbed or released? It was absorbed. That's endothermic, right? Energy is absorbed as it goes from a lower energy level to a higher energy level. Obviously, if it's going in the opposite way, so going this way, if it's starting up high and coming back down, that's going to be exothermic. The atom needs to release that energy from that electron, and it's going to give off that energy to allow the electron to drop back down to the surrounding. So that would be exothermic. Going to release energy. Questions on that there? Yes, sir.
Most of the time, it's energy.
Yeah, you can think of energy and heat sometimes as kind of the same thing. Yeah. And it is in some cases the same thing. Yeah. And again, in this case, what we're thinking about is sort of the flow of energy into the atom, which would cause those electrons. So when we shoot off the fireworks, for example, right, it's endothermic at the beginning, right, because it's got all the explosives in it, right? So as they explode, they're absorbing all that energy, right? That's going to cause all those electrons to gain that energy and jump up to higher energy levels. At some point, you're no longer exploding it, right? Going to relax back down, and in order for them to do that, the atom itself has to give off that energy. And again, that's where you get some wavelengths in the visible part of the spectrum that you see the colors that happen. So when we talk about energy levels, there are actually 7 different energy levels that we come across, and we refer to them as n. N is the principal quantum number. And n could have values of 1 through 7. And basically, n equals 1 is what is referred to as the ground state. That is the most stable state. That is the one that is closest to the nucleus. So the n equals 1 is the one that is closest to the nucleus. It is the lowest in energy. Anything above that, anywhere from n is equal to 2 through 7, those are what are sometimes referred to as excited states. So we will have electrons within the atom at different energy levels. And again, sort of that closest to the nucleus going to be that ground state. And that's what's referred to as the principal quantum number. Now, as I was saying just a second ago, basically electrons can only have certain energy values that allow them to, again, fully transition from one energy level to the next. And again, that is the idea of quantized energy we were talking about with the stairs. Here they went with the bookshelf there. So again, you could only put the books on a certain level, right? You can't put them in between, right? Because they're going to fall. And that's, again, the same idea as how electrons basically transfer. All right. So as we just talked about, as we go from a higher state of energy to a lower state of energy, that is an endothermic process. Energy is being absorbed. And as that electron transitions from a higher state of energy to a lower state, that's an exothermic process. And we're going to emit that energy. So if we look at this, right, we have an electron that moves from the first energy level to the third. Should it be absorbed or emitted in this case? So basically, n equals 1 is here, right? N equals 2, n equals 3, n equals 4. And again, energy is increasing as we go this way. So we're basically starting at n equals 1, and we're going to end up at n equals 3. So it went up in energy, right? So it had to absorb the energy in this case to do that. Electron falls from the third energy level to the second. That's going to be release, basically exothermic, right? Going to release that energy. An electron moves within the same energy level. No change, right? Because again, we only see the change as it transitions from one energy level to the next in this case. Any questions on that there? All right, so as I just mentioned, we have our energy levels and our excited states. So what we're going to talk about now is basically where we find electrons within the atom. Now, sort of an early model of the atom was, and this idea of electrons and sort of how they moved was one that was referred to as the Bohr model of the atom. And that is sometimes referred to as the planetary model of the atom, where it was thought that we had our nucleus and then we had these electrons in these pretty orbits, and the electron just goes around and around in orbits. Works really great for hydrogen, but as soon as you move away from hydrogen, where you have more than one electron, doesn't hold up the theory. So we do not do that here. Yeah, so that is not how electrons move. You can't just put your finger on the orbit and wait for it to come around the circle. They move really randomly. And the idea of the atomic theory that we're talking about here is basically a couple different ones, but one is Heisenberg's uncertainty principle, which basically says a particle like an electron, you do not know how it's moving or its location. And actually, the more you know about its location, the less you know about how it's moving. And the more you know about how it's moving, the less you know about its location. So what that basically, that and some other theories basically threw out Bohr's model to this idea that we really don't know how the electron's moving. We really don't know exactly where the electron is. The best thing that we could actually do is go, there's a really high probability that we could find an electron in this particular location. So if you remember, we saw that little picture, I think last time, there's like that pink sort of color that kind of fanned out, and that's like a probability map. And what we now think of in terms of electrons is we have our nucleus, and once again, we have electrons, which again are randomly moving around, not in orbits or anything like that. And it's more of a theoretical idea of how electrons are moving. They're what are referred to as wave functions, and a lot of calculus and nobody wants to do are way outside the scope of this class. But basically the idea there is something like an electron. We really don't know how it's moving. The best we could do is go, I think there's a really good chance an electron could be in this location. And as we know, since the nucleus is positively charged, electrons are negatively charged, we would have a pretty high probability of finding an electron near the nucleus. We still don't know how it got there. We still don't know where it's at exactly, and we still don't know how it's traveling. But if you had to pick a spot, there's probably a really good probability that you would find an electron somewhere near that nucleus. Just like if you kind of moved out from the nucleus at some distance, there's probably a lower probability of finding an electron out in that area. Doesn't mean you can't, and you might find an electron there. Again, don't know how it's moving and stuff like that. So what we did is, with a lot of information, moved away from Bohr's idea of these orbits where electrons are to this idea of probability maps. And that's essentially what these things are here. We moved away from orbits to what are referred to as orbitals. And orbitals are pretty much just that. They are calculus-based, mathematical-based probability maps of where you would find an electron in an atom. Would you actually see one that looked like any of those shapes? Probably not. But it's just, again, a probability sort of idea of where you would find it. So there actually are a few different types of orbitals we deal with. There are s orbitals. Now, s orbitals, there's only one type of s orbital, no matter what energy level you come across. So starting with actually the very first energy level, that n equals 1 level, that is where we actually first see s orbitals appear. And they actually appear, I'll just kind of sketch it maybe over here. There is what is referred to as a 1s orbital. The 1 means it's on the first energy level, and it's an s orbital. If you go to the second energy level, there is, surprisingly enough, a 2s orbital there. The 2 means it's on the second energy level, and it's an s orbital all the way up to 7. So there is an s orbital on every single energy level. There are also p orbitals. There's actually 3 different types of p orbitals. There are what are referred to as the px, py, and pz orbital. That is basically their location in 3-dimensional space, like in math, x, y, and z axes, right? There's one in the x orientation, y orientation, and z orientation. They do not start to appear until you get to the second energy level. That is where you first start to see the first p orbital, and there is a p orbital along the way, pretty much all the way up. So really here on the second energy level, spread that out a little bit better. On the n equals 2, there's a 2s orbital, and there are 3 2p orbitals. If each line represents an orbital, basically. There are d orbitals. There's actually 5 different types of d orbitals. Not important what the numbers are and the names of them are, but there are 5 different ones, and they do not start until you get to the third energy level. So on the third energy level, that is where you first start to see d orbitals appear. So I'll just come this way. On n equals 3, we have a 3s orbital. We have a 3p orbitals, and we now have 1, 2, 3, 4, 5 3d orbitals basically first start to appear. And lastly, there are f orbitals. There's actually 7 different types of f orbitals, and they do not start to appear until the 4th energy level. Running out of room, so I'll go up to the top here and do it. N equals 4. We have a 4s orbital. We have a 4p orbital. We have our 4d orbital, and that is where we first start to see our 7. I guess 7, 1, 2, 3, 4, 5, 6, 7. 4f orbitals first start to appear. Now, why is this important? How many of each of these things? Any individual orbital that you have can only hold 2 electrons maximum. Doesn't mean they have to hold 2 electrons, but they can only hold a maximum of 2 electrons. That would mean that if I filled up all of my s orbitals on any level, since there's only one, how many electrons could it maximally hold? 2. If I filled up all the p orbitals on any level, since there's 3 different p orbitals, each one could hold 2, how many electrons could it maximally hold? 6 electrons. Yeah, 2 in each. Just so we see it. 1 and 2, if those arrows are the electrons. 1, 2, 3, 4, 5, and 6 electrons. It could fill it up. If I have 5d orbitals on any level and I filled all 5 of them up, how many maximum electrons could I throw in there? 10. Yeah. And f orbitals, if there's 7 of them, if I fill them all up, how many could I put in there? I could put 14 electrons. So those numbers are really important when you write electron configuration as to how many you can put in there. By the way, when you are dealing with something like what we have here with p orbital, d orbitals, and f orbitals, they are also sometimes referred to as subshells, or depending on your book, sublevel. That would be the 4p subshell, which includes all 3 of the orbitals there. This would be the 4d subshell. This would be the 4f subshell. We don't call the s orbitals a subshell because there's only one orbital. Basically, we just call it an orbital, basically, in this case. So you'll sometimes hear the word subshell or sublevel. That is basically all the orbitals that are like all p orbitals on one energy level, all d together, all the f's together. You will also sometimes hear just the word shell or level. And shell or level is referring to everybody on that energy level. So when I talk about the n equals 3 shell, I'm talking about everybody that's there, basically, yeah? And how many electrons you could put in there, right? If I'm talking about an individual orbital, in this representation, it's any of the individual like lines, yeah? We could hold 2 electrons, basically, yeah? So for example, if I wanted to fill up the n equals 2 level, how many electrons could I put in there from the n equals 2 level? Well, this is the n equals 2 level, right? We could put 2 there, right? 4, 6, and 8. Yeah. If I filled up the entire level. How many electrons if I filled up the 3p subshell? 6 is correct. I think I heard. So all 3 of those guys make up the 3p subshell, where they each could hold 2 electrons each, which gives you 6. Yeah. How many electrons could I put in a 4f orbital? The answer is 2. It is 2. That's the trick question, because an orbital is each of these individual lines that can only hold 2. How many electrons in the 4f subshell? 14. That's the one you're looking for. That's the answer to that question. Yeah, so the lab manual likes to do that question, usually that question right there. So again, orbital, no matter where it is, any orbital, 2 electrons. Again, subshell, sublevel, that's usually a grouping of orbitals together, like in the P, D, or F. And obviously an orbital or a level is everybody on that level. Any questions on that there? By the way, obviously, if you had a question where it asks you how many electrons on a particular level, you may not want to count it all up. You could actually calculate it by doing 2 times n squared. So for example, if we did this n equals 2 level here, the n is actually the principal quantum number, so that would be 2 squared times 2. That is 4 times 2, which is 8. Yeah, and that's what we saw earlier. You could go all 8 if you went the entire level. Yeah, so if you want to do 4th level, you would do 4 squared times 2, basically. So that's 16 times 2 is 32. So if you counted up everybody here, if I had the lines, the F lines aren't there, but you could put 32 electrons on there. A lot easier than trying to draw it out and count them all up that way. So that works for if you want to figure out how many electrons are on a level. So what we see here is the energy of all these orbitals in hydrogen. And what we see is when you have 1 electron, all the orbitals are essentially the same in terms of their energy. Everybody on the second energy level is the same. Everybody on the third is the same. But when you have more than one electron like hydrogen that we see in hydrogen, you start to get a lot of electrons near each other, right? Electrons which are negatively charged. Do they really like to be near other electrons? Not really. So what happens is you get a lot of electron repulsion. And what happens if you look at this when we have just 1 electron versus many electrons, there's actually a change in the energy of these orbitals. And that's really important because electrons go into the atom lowest energy first, and then the next lowest, and then the next lowest, and until everybody's filled with how many electrons that you need to put that. So you can see we go 1s first, then we would go to 2s, 2p, 3s, 3p, and this is where the difference is. Actually, the 4s orbitals are actually lower in energy than the 3d orbitals. So the 4s orbitals would actually get the electrons first, and then they would go to the 3d, and that pattern follows up here as well. So when we write something like electron configuration, there are 2 things that you really need to know to be able to do that. And this is one of those things, and this is the same thing. This is something that you can create really easily for yourself. But if you know that an s orbital can max out with 2 electrons, a p subshell can max out with 6 electrons, a d subshell can max out with 10 electrons, and an f subshell can max out with 14 electrons, and you know this little chart, you should be able to write any electron configuration that you need. You start up here, and you basically just keep going, and then you zigzag back, and you just keep going, and you just keep zigzagging until you basically fill in however many electrons you need. How can you make it? Pretty simple. You do it this way. S's start on what energy level? 1. So you write 1s, right? P start on what energy level? So you go down to the right, 2p. D start on what energy level? 3. Go down to the right. And F start on what energy level? Down to the right. 1, 2, 3, 4. All you have to do now is just fill in the numbers with the letters underneath each of those. So that's like 2s, 3s, 4s, 5s, 6s, 7s, 2p, 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d, 4f, 5f. I just recreated it just by doing 1, 2, 3, 4. You draw your arrows, yeah. And you basically just recreated pretty much what you need, and you can obviously continue on and stuff like that. So that is something that you need to know. That is the order that we just saw on that previous page there of how the electrons go into the atom and the maximum number of electrons. That allows you to write electron configuration. So why don't we just do one here to finish it up, just to show you what it is and what it looks like. We'll do hydrogen here. Hydrogen is atomic number 1, which means it has 1 proton, and that would mean that neutral hydrogen would have 1 electron as well, right? So again, we start with our chart. Let's make my chart real quick here. Good enough for now. So we always start up here and we're going to go this way. And again, S could hold 2 electrons, P subshell 6, D subshell 10, and F subshell 14. So we would write 1s1, and that is the electron configuration for hydrogen. The first number is the N number, basically. That is the energy level. That is basically telling us that we're on the first energy level. That is the orbital, our subshell that the electron is in, and that is how many electrons are in it. I have now put 1 electron in my s orbital. That is the way you should write it. Big 1, lowercase s, superscript 1 on top. No dashes, no commas that people like to do, weird things and stuff like that. While we're at it here, let's look at helium. By the way, how many more electrons could that s orbital hold? 1 more, right? Because we kind of drew a picture. We basically just put 1 electron in there, right? So we have room for another. That's helium, by the way. Again, we always start up here. And that's going to give us 1s2. Yeah. Again, first energy level in the s orbital, 2 electrons hanging out there. That would be if we drew our picture, 1 up, by the way, 1 down for reasons not important for our class, but that is how they go in there, like that. That is clearly filled, right? If I had to put more electrons in, where does S go next? Yeah, we zigzag back there to our 2s, right? So dare I say our friend lithium, which is 3. We again start up here. That is 1s2. Now we go to 2s1. Grand total of electrons that I put in there, count the top numbers, 2 and 1 is 3. Yeah. I have how many electrons on the first energy level? How many on the second? 1. Yeah. So I got 1 on the second energy level, 1 on, or 2 on the first. If we looked at that, this is what that looks like. I could put how many more electrons into my 2s orbital before I have to move on? 1 more, right? And dare I continue on? I don't know. What is that? We got beryllium there, which is 4. So that would be 1s2, 2s2 for beryllium. And again, that basically would then put that next electron in there. At this point, we now have 2 electrons in the second energy level, 2 in the first. Where would I go after that, by the way? That's where I would go next. And I could put how many in that subshell? Subshell, I could put 6, 2 in each, yeah? So the next 6 guys, electrons, would be entering into that subshell, right? And again, at that point, you would then continue on to the next one if you needed, and so forth, and fill it in until you're done. Any questions on a really quick version there of that? Yes. I'm sorry, say it one more time. I'm really sorry, I can't hear what you're saying. I'm sorry. Yeah. Oh, it does, because there's actually no electrons that will go past that. So pretty much that will cover all the electrons on the periodic table that you need. They technically can, but that will cover pretty much everybody on the periodic table. And we'll talk about next time that